Hi guys, I'm gonna show you how to do some of these exercises from 2.2. The first one was you had to show that if you take the difference of these two sets and then take the further difference of this set, that this is equal to A minus C minus B minus C. Now there are several ways that you could do this, but I'm gonna only show you one because I think it's the best, easiest and least prone to error. And that is using truth tables. But for instance, you could try to make Venn diagrams, and it's a good practice to find exactly which areas are these. Okay, and in fact, I'll show you that you can do this with truth tables as well. So it's easier actually to work with truth tables. So let me explain how. Sorry, there's another thing, of course, you can do is prove that, as in the book, sometimes they show you how to do this. That this set is contained in that set and vice versa. Meaning, how do you prove that? You take an element in this set and then show that it's in there. And also, what you also have to prove, because you need equality, is to take an element here and show that it's in there. Okay? But I don't practice this thing, I think, because truth tables are so nice that there's no need to do this more reasoning. This is much more structured. Okay, so that's A, B, and C. Now, it's a truth table, membership table correctly, so that means we have 8 possible configurations, right? And they correspond to the 8 regions in a Venn diagram. And I'll come back to that when we solve the problem. So then we have 1, 1, 0, 0, 1, 1, 0, 0. Be very systematic here that you don't forget any situation. Okay, and now we have to just find all the parts here. We need A minus B. And that means when will be you in that set if you're a 1 in the A column and a 0 in the B column. And so we see that this happens exactly here, right? So this is you're in A but not in B. Here you're not even in A, here you're in both. So, okay, so we get a 1 and 1 here and everything else is 0. And now we do minus C. And what is that? Okay, sorry, that's not what I meant to say. I mean to say I'm A minus, sorry, we're right. What I mean to say is A minus B minus C. Okay, so what we have to do is we're looking for something that is in here, so a 1 here, but not in here, a 0 there. Now there are only 2 1s in this column, so, and I need to have a 0 in the other column, and that's exactly only here that this happens. So we see we get a 1 here, and everything else is 0. Okay. What about that's the left-hand side. Now we have to show that's the same as the right-hand side, so we also have to calculate A minus C. We're looking now for 1s in this column and 0s in this column. So in this column, so this would be these two cases, 1 and 1, and the rest is 0. We also need B minus C, this guy, and that one we need 1s in this column and 0s here. So I see here a 1 and a 0 combination, here is a 1 and 0 combination. So that would be a 1 here and 1 here, and everything else is 0. And finally, what we need to do is take the difference of this of that, meaning we need something that is in here but not in here. So we need a 1 here and a 0 there. Now there are 2 1s only, but only one combination where we have a 0 in this for the second row. So this will be a 1. And everything else will be 0. And now, so this is A minus C minus B minus C. And now the question is, are they the same? Well, which ones? Well, is this the same as that? And you see it is the same. Now, coming back to the Venn diagrams, so we have a Venn diagram here, so we are inside a big universe. And so what are we dealing with? We have exactly 8 regions, if you count, right? 1, 2, 3, 4, 5, 6, 7, 8. And which is the region that we are dealing with? So let me make it perhaps in orange here. The correct region, or the only region that the left-hand side and the right-hand side are both only one region. So what are the regions? Well, remember each of these 8 rows corresponds to exactly one region. And you can figure out which region is this. Let's do it for the orange guy here that we just lined up. That is an element. This region is the region in which your R in A, so your R, oh, I did not say what A, B is. This is A, this is B, and this is C. So you have to be in A, so you are in this guy, but you're not in B, so you're outside this part, so not there, and you're outside C. So the only thing that remains is this one, right? So this is the region that they both are equal to. Now, that's not the proof, right? Because the proof, if you have to prove it with Venn diagrams, you have to then first calculate what is this region. So I'm just going to do one case just to see how it works. So let's see. I want to first find what is A minus B. Everything that is in A but not in B. Well, there are 2 regions, so I'm going to do those in green. So I'm doing A minus B. Okay. That is everything that is A and not in B. Well, this is in A and not in B, but also this. So we have dealing with these 2 regions here. Okay. And what is then the actual thing that we want is this one. Everything that is in the green but not in C. So everything that's in the green and not in C, and you see that is exactly the orange guy that I claimed it would be. So perhaps I should not have made it blue, I should have made it orange, right? Because that's, my claim is that these are the same here. Okay, so that's how you prove things with Venn diagrams, but you see truth tables are much more systematic, and you won't make any mistakes. If you're careful, you won't. It's much less. It's harder to have mistakes. That's not the correct way to say things. With double negatives, but okay. All right, 26. Number 26 is the question. Draw Venn. So here they want you to draw Venn diagrams. So. Okay, I'm going to use the one that I have already. I'm lazy, so I can erase this. I'll take out the little. Ooh, that's the one thing I didn't want to touch. Okay, I have to make my C again. So, what are the things that we want to do? 26A. It's the region or the regions, because it doesn't mean that it's just exactly one region. It is A intersect B union C. And again, I'm going to use colors. So let's start with B union C. What is B union C? Everything that's in B and C. So everything that's in B here, but also everything that's in C. So all these guys are B union C. Okay. Now I have to. What I really want is this guy. What is that? That's everything that is so as well in A as in B union C. So the things that are in A are these guys here. So of these orange regions, we're talking about these 3 guys. So if I would shade it, it would be these 3 guys, right? Okay. Oh, the other one, I'm not going to do all of them. I want to do one a little bit perhaps. Oh, let's do B, the complements. A bar intersect B bar intersect C bar. Okay, so I'm gonna try to get rid of my colors. Hopefully this works. Yep, nice. Huh? Okay, so let's do A bar. What does that mean? Everything that is not in A. Now be careful. Now this also includes the outside part, right? Not just the things in B and C, but also the outside part. This is gonna be a lot of coloring. If you like coloring, this is a nice job. It's a nice question. I've never was good at coloring. You see, I'll go always out of the lines and so on. Okay, so that's the complement of A. Now, okay, I have to do this also for B and do that in blue. Everything that is not in B, so everything that is outside. So let me circle B and then go everything out there. I don't know whether it's going to be so many colors that we don't see anymore what is what. Okay, then let's do complement of C. So everything that is outside of C. Okay, so everything that we get here. Okay, so now the colors are getting a little bit too much, right? So I'm gonna now use zigzags for my actual intersection. So I need something that is both blue, green, and orange. Okay, I told you I got so much stuff. I see one here. This region is definitely one of those. I'll just start them. Is there anything else? No, because let's see. This is blue and orange. This is just orange or red. Well, actually it's pink, I guess. Sorry, blue and pink. This is pink, pink and green, only blue. So the only thing I seem to getting is this guy here. So the outside, okay. So in the Venn diagram, so if you actually, I know this is, how do you present this, right? How do you make this neatly? How do you answer the question like that? We solved it, but now how you have to give the answer? I guess you have to draw it again, kind of thing. I'll make it small now because I know what is going to happen. So A, B, and C, and we're dealing with this region here. Yeah, I shouldn't shade it because shading often means it's not part of it. So what we sometimes could do is number them and say this is region, this is or put a mark in there, like this is region star. Okay. So what else? Well, let's do the third one too. Okay. I start liking the coloring part. Oops, I got rid of a dot, but now I got rid of too much. See, I got rid of too many things. I got rid of B. There you go. And so C, what was that? A minus B union A minus C union B minus C. Okay, so there we go again. A minus B, let's do that in pink. Well, it looks like it should be red. Huh? Okay, I'm gonna call it red because on top you see it looks like a red pencil. So A minus B, everything that is in A but not in B, we mark. I'm gonna do now this, I'm not gonna color it, well, I should color it a little bit, so I'm gonna do a little bit of colors in there. A minus C, let's do that in green. Everything that is in A but not in C, so I stay outside of C, but I stay inside of A. Okay, so. And then finally B minus C, so that would be blue, I guess. Everything that is in B, but not in C, so I have to stay outside of C, so that would be this. And now the union is actually everything that has been colored. Okay, so the union is everything that has a color now. So if you want, I'll do it in yellow. That would be all these stuff. Everything that has some color is this whole guy. Oh, sorry, I forgot to indicate that this was blue. Okay, that's just. I mean, it's not getting a little bit too much infantile, right? What we're doing. Okay, so let's move on to the last question, and this is something that I want you to do because we're going to do a quiz on this, so you'll see that is also an exclusion principle. So inclusion, exclusion. There's also going to be a review that you can see in today's lecture. Inclusion, exclusion. I remind you again that's a formula about how many elements are in the union of two sets. And that's the number of elements in the first set plus the number of elements in the second set. But if you only look at those two things, you count something twice, namely everything that's in the intersection. So you subtract. Okay. And so this was in 6.1. That's a chapter that we're not going to deal with. That's for discrete math 2. But this particular problem you can deal because we have learned about it. So here it says every student in discrete math class is either a computer science or a mathematics major or a joint major. Okay, so the majors are what was it? It's either computer science or math major. Okay, so this is the students in this class, discrete math. So how many students are in the class? So there are two, the major CS major. We know how many how many guys are 38. There are 38 computer science students. There are 23 math students, and there are joint majors. How many are there? There are 7 joint majors. So let's call these perhaps sets. So C. Well, I'm going to use the first capital letter, so that makes me. So I'm going to use C, M, and J for my sets. Or J, I don't even need. That's well, right. So C and M. So again, I just want to write down the same formula again. C union M. Now using these two particular sets. Oh, I'm sorry. This is okay. Let me C union M. That's the number of elements in C plus the number of elements in M minus the number of elements C intersect M. Okay, so the number of elements in C is 38, the number of elements in M is 23, and the one in the intersection is 7. So the answer is just this: 61 minus 7, 54 students. Okay? Alright, so that's it. And so the only problem with this inclusion and exclusion is to set it up correctly, define the sets, and figure out what information you have. Now, in these straightforward applications, you see you get everything about the set, the two sets, the number of elements in the set, and number of elements in the intersection. But sometimes, perhaps, you know how many there are in the union and how many there are in each separately, and then you can find out how many in the section. So this is a formula in which you should think of this not just a formula about the number of elements in the union, it's a formula about that links these 4 quantities. And if you know 3 of them, you can find the 4th one. That's the whole idea. Okay, that's it for the homework.